Hello everyone, I am Zihao Yu from Institute of Computing Technology, Chinese Academy of Science. Today I will give a talk about performance isolation for the multi-core architecture. First, let's have a quick recap of the history of control in computer architecture. In the 1950s, microprogramming is proposed to simplify the design of CPU controller. And in the 1980s, RISC became popular. With RISC, the controller become very easy to design. And so people, they pay more attention to the data path optimization instead of paying more attention to the design of the controller. But after the multi-core emerges, this will lead to some problem. So in the multi-core architectures, different cores share some resources. For example, the last level cache, memory, and I/O bandwidth without any control. This may cause some uncertainties. When a latency critical application and another throughput-oriented application run on different cores simultaneously, the hardware cannot identify the source of the software source of the request. This make it hard. This make it difficult for the hardware to control which requests go first. In reality, in the data center area, this will cause QoS violations. Researchers of Google, they conduct a lot of experiments, and they try to co-locate different applications on the same server. They found that in most of the time, the application suffer from unpredictable performance degradation. In the aviation area, this may cause unpredictable worst-case execution time. FAA published a white paper last year. In this white paper, they introduced this kind of experiments. They read 4 kilobytes data from memory. They found that when a single application is running, the execution time, the distribution of execution time is very concentrated. But when there are multiple applications running together, the execution time becomes unpredictable. This makes it very hard to satisfy the real-time property. So in the aviation area, the multi-core is usually disabled. But this does not solve the problem. The key point is to achieve the performance isolations in the multi-core architecture. However, as mentioned before, the hardware cannot identify the software source of a request. This makes it very difficult to perform further controls. Actually, we can learn something from the network area. Labeled network, for example, MPLS, they use a specific header to carry the user demands. Switches can identify the user demand of a package by examining these specific headers, and then performs further process to this package. This will help to reduce the uncertainties of the network. On the other hand, a computer can also be viewed as a network. Hardware components will communicate via packets. For example, take DMA as an example. The device issue and DMA packets, and this packet will be translated to NOC packets and then sent to memory. IPI will also be sent by QBI packets. So we can ask the following questions. Can we apply the labeling mechanism to the microarchitecture? The answer is yes. So to achieve performance isolation, we first proposed a new architecture model called labeled OMA Architecture. The key idea of, or LVNA for short, the key idea of LVNA is to convey the software information down to hardware by labels. It has 4 properties. The first is each request has a label. Second, each label is correlated with a software entity, for example, process, thread, or even variable. And third, labels are propagated in the whole machine. And last, we use software-defined control logic to provide differential service by label-based rules. But the Arduino does not define how to use control logic to actually achieve performance isolation. We propose part programming architecture for resourcing on demand. And as a labeled architecture, we first add label registers to each virtual machine, and then allocate labels to each machine, and then attach this label to all of the requests this virtual machine sends. And to make good use of the control logic, we use the we use the label-based control tables. Each column of the table corresponds to policies. And when a request comes, the control logic will use the label attached to this request to index the control table. This will retrieve a set of control policies, and these policies will be applied to this request. And finally, to manage the label registers and the control logic, we add a new model called a Platform Resource Manager, or PRM for short. PRM is a linear space formula, and to manage them in a unified way, we abstract the label register and the control logic into files. After that, PRM can access them by file operations. So we give a brief introduction about how to reconstruct the Rocket chip project into a labels architecture. First, we add the label registers to each tile. And this is achieved by adding a new member's DSID into the bundle definition of the tile link. So after that, the label will be propagated in the whole tile link network. And we can also add a control logic to the share cache to perform a way partition. And to convey the label out of the tile link network, we also modify the tile link to AXI converter to convey the label to the user signal of the AXI protocol. After that, we add another control logic before the DRAM controller, and in that this control logic supports address mapping to manage physical address space, and it has the label token bucket to provide fine-grained memory bandwidth control. At last, we add a PRM module to manage this resource. So this implementation is already open source. So for the overheads, there are only less than 3% extra code to add to the Rocket chip project. And among them, there are 16 lines of chipset code to add labels into the Rocket chip. And for the resource overhead, it's less than 5% for all the control logic. And if we use a compressed core, for example, Boom, and the resource overhead will be much less. And additionally, according to the timing report, there are no performance overhead for the critical application. And there are two demos. The first we call the label hype. For a traditional server, they use the software hypervisor to provide functionality, to provide functional isolation between virtual machines. But with the help of label, we can push some basic functionality of software hypervisor down to hardware. So in such a situation, the virtual machine is functionally isolated by the labels. This can remove some runtime overhead of the hypervisor. For example, they change the hypervisor, they enter and exit the hypervisor mode. This will cause some cache flush or TLB flush. So, but the label height, it do not have this problem. The second demo is about the memory bandwidth isolation. So we first run an application alone. Then we run it with an attacker running in another virtual machine. So we can observe a dramatic performance degradations. After that, we will run these two application with the attacker and with the label token bucket enabled to protect the bandwidth from the attacker. So at this time, although the attacker is still running, the application can reach the performance as it runs alone. So for the Alvina, there are a lot of things to explore in the system stack. And a great step is that we are planning to tape out with the TSMC 14 nanometers next year. And to summarize, Alvina is a model of label architecture, and partly is a case of Alvina for performance isolation. And label RISC-V is an open source implementation of Alvina. And as a model, Alvina we may also apply Alvina to other areas for us to enable some interesting research, for example, security and other things. So we hope all of you can join us to explore the future of Alvina. So this completes my talk. Thank you.